This is part number 2 of Unit 4 in college algebra, in which we talk about parent functions and their transformations. In the first lesson this week, we're going to talk about quadratic functions exclusively. So you should recall the quadratic function is in this form, where f of x is equal to ax squared plus bx plus c. A, b, and c are real numbers, and a cannot be equal to 0. If a were equal to 0, well then this whole term would disappear and we'd be talking about a linear function. So there's a quadratic function in what we call standard form. And that's helpful for us if we're looking for a solution and we want to use the quadratic formula. But if we're graphing this function, a lot of times we have the function written in what we call vertex form. And this is the vertex form of a vertical parabola. Instead of using a, b, and c, we use a, h, and k as our parameters. Now this a value here is going to be the same as this a value here. In a sense, it's kind of like the slope of the quadratic, although we definitely don't want to call it a slope, but it specifies the shape of the quadratic function, the u shape itself. But the h and the k actually are coordinates of the vertex. And the vertex of a parabola, you should recall, is either the low point of the u shape or the high point of the u shape, depending on its orientation. But that's the vertex. And so if the h and k allow us to find the vertex, or the location of the parabola, it's this a value that gives us its direction and size. So let's see how we can get the vertex form of an equation if it's given to us in standard form. In this particular question, we're being asked to find the vertex and the axis of symmetry. We'll talk about that in just a second. And the vertex is very hard to locate when the equation is written in standard form. Now I'm going to use a technique called completing the square in order to rewrite this from standard form to vertex form. And I would recommend doing a search on YouTube for this phrase in case you're not familiar with it after we walk through this example. Now completing the square requires us to focus on the first two terms of this quadratic. What I'm going to do is I'm going to rewrite this function with a little bit more space. So I'm going to write 2x squared plus 8x. I'm going to leave a bit of a gap and add the 5 on the outside, because what we're looking for is a number that's going to go here to complete the square trinomial. Now this technique, completing the square, generally only works when our a value is 1, and you may notice that on the inside of this grouping symbol before I put that plus sign here is that there's a GCF. And we're going to factor that GCF out. And so now I'm going to place the 2 on the outside. I'll have x squared plus 4x. This is going to give me an option to find the correct number to complete the square trinomial. And I still have this plus 5 that's hanging out here. Now the whole completing the square process relies on this formula, and this is one you've got to have memorized. And that's b squared divided by 2, or half of b squared. Now it's not the original b value that we started with, it's this new b value that we've got after rewriting our equation so far. In this case, this b value is 4. And let me just clarify this here. It's not b squared divided by 4, but it's actually b, half of b squared. Sorry about that. So there we go. b divided by 2, that quantity first, then square the result. So our b value is 4. We're going to divide that by 2 and square it. Well, 4 divided by 2 is 2, and 2 squared is 4. The value that we're using to complete the square trinomial is 4. And that makes a square trinomial on the interior of this expression. I'm going to slide this side note over a little bit further. Get that out of the way. Now, we can't just add this 4 to this side of the equation without keeping the equation balanced. So a lot of times when we add something on the right side of an equal sign, we'll add it to the left. But I really don't want to add anything to the left side of the equation because the left side of the equation is just f of x. It's the description of our function. So what I'm going to do is I'm going to subtract a value out here on the right-hand side, and that will effectively balance the equation too. Whatever I've added on this side of the equation, I can immediately subtract from the same side of the equation, and the equation will remain balanced. What we must keep in mind, though, is that while we use the number 4 to create a square trinomial on the interior here, the value of this 4 is doubled because of the multiplier that's out front. So while we have plus 4 on the interior, that really has a weight of 8. And if we added 8 to this side of the equation, I have to turn around and subtract 8 from this side of the equation as well. So it's a bit confusing. It could be a bit intimidating at first, but as long as you think of the big picture here about balancing the equation, that should hopefully make sense with a little bit more practice. Now, the whole reason why we spent our time using the complete the square method to rewrite this is because this quadratic trinomial right here factors very nicely. And it factors into x plus 2 times another x plus 2. And in all cases, when we complete the square trinomial, when we choose the correct value back here, we're always going to get a pair of binomials that are the same. When we have a pair of binomials that are the same, then we can rewrite this final expression this way: 2 times x plus 2 squared. Whatever this binomial pairing was, we can write that a single time, squared, and we can combine the two numeric values or constants at the end. 5 minus 8 is negative 3. And now what we've done is we've rewritten the original standard form of the equation into vertex form. These two are equivalent. So what's the vertex? Well, the vertex, the location of the peak or valley of this particular parabola, is located at negative 2, comma, negative 3. We use a negative 2 here because, as the instructions indicated back here, we want the opposite of h being labeled in our grouping symbol. So negative 2, negative 3 is the vertex. And the axis of symmetry is the vertical line that goes through our x coordinates. So we'll just write this as x equals negative 2. These two numbers are always going to be the same. That axis of symmetry gives us this imaginary vertical line that acts as a mirror, if you will, or cuts our parabola in half. Now we've got this parabola that's located at negative 2, negative 3, which is right here. Its vertex is right there. And with an a value of 2, this is telling me that the graph of this parabola is going to open up because it's a positive number, and it's going to be twice as tall as usual, as a usual parabola. And a parabola normally is shaped like this, where we have a coordinate here at this origin, and right 1 unit from the origin and up 1 unit, because 1 squared is 1. We would go right 2 units from the origin and up 4 units, because 2 squared is 4. So 1 squared, 2 squared. If we were to step 3 units to the right from the origin, 3 squared, we would have to run up 9 units to plot that coordinate. And this is where the normal shape of a parabola comes from. We would mirror that on the left-hand side. But since this graph is twice as tall from the origin, or new origin if you will, when we step to the right 1 is not just squared, but it's doubled as well. So 2 times 1 squared is 2. And to the right, instead of going up 4 units, which normally would have been 2 squared, we double that, call it 8 units. And now we have a vertical step of 2, another vertical step of 8 from this imaginary origin, and we can duplicate these values on the left side of our axis of symmetry. And now we've got the graph shown. The alternative to graphing this way would be to pick arbitrary values for x and substitute them into this original equation, which would be fine. However, you'll notice that the x values of importance are down here at, say, -2, -3, -4, and -1 and 0. If we just started picking random x values, it's unlikely that we would have picked those 4 or 5 key data points. And so this vertex form is nice for us because it gives us proper location to look at in order to graph this function. Now, as it turns out, we don't have to go through the completing the square process to find the vertex or even to rewrite in vertex form. This particular pair of formulas allows us to identify the h and k value with just a mini computation, and that's the opposite of b divided by 2 times a. So here again, instead of going through the entire process of completing the square, let's see if we can find our h coordinate and then our k coordinate. Well, we are in standard form, so in order to calculate h, we would take the opposite of b, which is 6, divided by 2 times a, which is -3. And so that becomes -6 divided by -6. It looks like our h value is 1. Now that we have our h value, we can calculate our k value by simply substituting this h value into the formula for the function. And that would be -3 times 1 squared plus 6 times 1 plus 1, which comes out to be 4. And so now, rather quickly, we've been able to rewrite this function in vertex form because the a value of the vertex form is the same as the a value in our standard form. So we've got -3. And we've got x minus 1, remember it's the opposite of the h value, plus k, which in this case is 4. We will reuse the k value as it is. So as far as the questions go, we needed to first locate the vertex. Well, the vertex is located at 1, 4, 1, 4, or the opposite of this -1, 4. The axis of symmetry, that's easy to do. That's going to be x equals 1. And does the graph open up or down? Well, because the a value equals -3, we know that the graph opens down, and it's essentially 3 times as tall as a standard quadratic function. So let's take a look at example down here. Can we graph this quadratic function using its vertex, axes, and intercepts? And I'm looking at this equation, and I think I want to modify it. Let's change this to +8. And we can tell a lot about this function, whether it opens up or down, by simply looking at the a value. Now, we are written in standard form, so the a value is 1. So with an a value of 1, we know that it opens up, and it's what we would call a standard height. It's not taller or shorter than usual. So that much we know by simply looking at the a value. We would need to find its vertex to locate this graph, unless you want to guess and check with a bunch of different x values. We should find its axis of symmetry, the x and the y intercepts if they exist. So let's go for it. In part A, I'm going to use completing the square to do this, although you could use the formulas from the last example. For completing the square, we have x squared plus 6x plus 8, giving myself a little bit of room here. The a value inside this grouping symbol is already 1, so we can use the shortcut half of b squared. So half of 6 squared is what I've written here, not b divided by 2. That is a 6. Well, half of 6 is 3. 3 squared is 9. Now, if I'm adding 9 to the interior of this grouping symbol, then I'm going to subtract 9 from the exterior. Not 18 this time, but just 9, because there is no multiplier outside of this grouping symbol. I also recognize that this square trinomial can be rewritten as x plus 3 twice, and 8 minus 9 is -1. So if our function f of x is equal to the quantity of x plus 3 squared minus 1, then that tells me that the vertex is located at negative 3, comma 1. The axis of symmetry is x equals negative 3. We know that our x-intercepts occur, well, let's start with the y-intercept because that's what they asked us to do first. So let's say our y-intercepts occur when x is equal to 0. All y-intercepts are found when x is equal to 0. So let's evaluate the function at 0. When we evaluate the function at 0, that would be 0 plus 3 squared minus 1. So 0 plus 3 is 3. 3 squared is 9. 9 minus 1 is 8. So we have a y-intercept at 0, comma 8. That's our y-intercept. So we've got a vertex, we've got the axis of symmetry, we've got a y-intercept, and now x-intercepts. Well, x-intercepts occur when y is equal to 0, and f of x is just another notation for y. So when we set the entire equation equal to 0, we've got 0 equals x squared plus 6x plus 8. To find those zeros, we tend to factor. And I like x, let's see here, plus 4 and plus 2. That means that at x equals negative 4 and at x equals negative 2, the function would be 0. So we can say that our x-intercepts are at negative 4, 0, and negative 2, 0. I just realized something. This original problem had a minus 6, so we'll go ahead and change this problem too. You could try this problem one more time with a minus 6 as it was originally written, and you'll see how the factors change and the location of our intercepts change just a little bit as well. But that's not overly critical for this example. If I plot my vertex at negative 3, 1, sorry, that should definitely be a negative 1. We do use the k value as it was given. So negative 3, negative 1, we have our vertex here. We have x-intercepts at negative 4, 0, and negative 2, 0. We have a y-intercept at 0, comma 8. Those 4 data points do a pretty nice job of locating the position and direction of this graph. I will also stress that from this new origin, or from this vertex, if we were to step to the right 2 units, we would normally go up 4 units because 2 squared is 4, and there's another point on the graph. If we had stepped to the right 3 units, 1, 2, 3, we would have gone up 9 from that position to land on another coordinate. And as it turns out, that's exactly what we've done. Up 1 unit to the origin, and then up 8 units to our x-intercept, our y-intercept, and we've now located that position. And because of this x equals negative 3, our axis of symmetry, we know that any data point on the right side of this dotted line can be mirror copied over to the left. We've got this data point, and then this data point, 3 units to the right, 3 units to the left of that axis of symmetry, 2 to the right, 2 to the left, 1 to the right, and 1 to the left. So now we've got a nice collection of data points that we can connect with a smooth and continuous line. Depending on how you sketch this in, obviously I'm using these short strokes with the pen, but I'm trying to make it look as smooth and continuous as possible. And now this graph represents the parabola through those points. So that's a lot of work to address part A, but I think it's a nice analysis of what we've got. For part B, the domain and range, well, the domain, all x values that can be used in this function or that may show up in this graph. Well, as it turns out, any x value is permitted in a quadratic, so any x value, as long as it exists as a real number between negative infinity and positive infinity, would be good for use in the domain. As far as our range goes, well, we can't use all y values in this graph. The smallest y value that we're going to encounter is here at negative 1, But then as we continue in either direction on this parabola, the y values will simply increase. So we'll never see a coordinate on this graph that contains a y value smaller than -1. So we'll say that the y value for our range must exist from the number -1 up to positive infinity. And lastly, to reconnect with older notes, where is this function increasing and decreasing? Well, along this yellow pathway, the function is increasing. Along the green pathway, the function is decreasing. The y values are getting smaller along the green path. The y values are getting larger along the yellow path. So we will say that the function is increasing. Even though we're looking at the y values, we express our answer in terms of x. So they increase along all x values that are from the position, not including -3, but up to infinity. So again, all of these x values from -3 upward, that's our increasing function. And then for our decreasing, I shouldn't say function, but decreasing portion of the function, is decreasing for all x values that are from -infinity up to -3, but not including. And again, these are decreasing because any x value from here back shows a section of the graph that was decreasing. So with this as an example, I would like to challenge you to complete the next question on your own. Certainly you can complete the square to find the vertex of this expression, or you can use the formula from a little bit earlier. But go ahead and repeat the process that we just did with the last example on your own, and resume playback here in just a moment to check your work. In this example, I elected to use completing the square again to answer part A, but I wouldn't be surprised if any of you used the formulas from the second example of the notes here. In completing the square, I grouped the first two terms and factored out the number 2. It's a bit unusual because it's not really a common factor, but it had to be divided out in order to complete the square, and that leaves us with x squared plus 1/2 x. Now that 1/2 x, if I divide 1/2 by 2, that's 1/4, and 1/4 squared is 1/16. So 1/16 completed the square, but 2 times a 16th is the weight of that value. That's 1/8. So by writing 1/16, that's the same as adding the weight of 1/8 to this equation. So I immediately turned around and subtracted 1/8 from the equation to keep it balanced. In factoring, it's 1/4 that will be used as our factor here. 1/4 times a fourth is 1/16, and 1/4 plus 1/4 is 1/2, and that is what gets us back to our middle term here. And so our factor is x plus a fourth squared. 1 minus 1/8 is 7/8. So therefore, our a value of 2, our h value of -1/4, and our k value of 7/8 are all obtained by looking at this vertex form. The h value is -1/4 because it is the opposite of the sign indicated here. The a value of 2 tells us that the graph opens up and that it's going to be twice as tall as normal. The vertex is located at -1/4, 7/8. The axis of symmetry, therefore, is x equals -1/4. Our y-intercept, which is found when x is equal to 0, was found by substituting 0 in for x in our vertex form. That calculates out to be 1. And for our x-intercepts, this is kind of interesting. When does the function itself ever equal 0? Well, it doesn't. If I set the equation equal to 0 and subtract 7/8 from both sides and divide by 2 and then try taking the square root, well, I can't take the square root of a negative number and obtain a real number result. Since there are no real solution, then there are no real roots, and therefore there are no x-intercepts. That shouldn't be a surprise, because if the vertex was located at 0, 1, if our vertex was at -1/4, 7/8, and we had a y-intercept at 0, 1, and we know that the graph is opening upward, then clearly the graph will not touch or cross the x-axis. Moreover, I would like to stress that from this vertex, if we step to the right 1 unit, now the scaling's pretty large here, but if we step to the right 1 unit over here, we'd have to go up 2 units in order to reconnect with the graph, and 2 units up was actually 8 grid lines. 1 unit to the right was 4 grid lines, and we can actually see how the graph will reach that point of the on the picture as well. The domain, again, is all x values from negative infinity to positive infinity, and y values exist from 7/8 up to infinity because it's an increasing function. It increases on the x values from negative 1/4 to the right, so from negative 1/4 towards infinity, and it's decreasing from negative infinity to negative 1/4. Now, you may have noticed that I've already finished the next example too, so I'll just talk about it as well. One more time, I'm using completing the square to rewrite this into vertex form. So I grouped the 3x squared and the 6x together, and I pushed the negative 3 out front. I factored it out of that group. And that left me with x squared minus 2x. Now, half of negative 2 is negative 1, and negative 1 squared is positive 1. So positive 1 was the number that was used to complete the square trinomial. Now, even though I wrote down the number negative 1 here, this negative 1 is being multiplied by negative 3 in this expression. So the positive 1, when written, really carries a weight of negative 3. Negative 3 times 1. So with a weight of negative 3 being added to or taken away from this side of the equation, I had to add 3 to this side of the equation in order to keep it balanced. Therefore, in our vertex form, we have an a value of negative 3, a k value of positive 1, since that would be, the h value of positive 1, that's the opposite of the number shown in the grouping symbol, and a k value of 4. Therefore, our graph will open down. It's 3 times as tall as normal. Its vertex is located at 1, 4, and its axis of symmetry is at x equals 1. The y-intercept occurs when x is equal to 0, so that calculation is shown here. When x is changed to 0, we can simplify and find that y is equal to 1. So we now have a vertex at 0, 1. But for our x-intercepts, where y is equal to 0, this gets to be a bit tricky. If I used general algebra, I would have to subtract 4 from both sides of the equation and then divide by negative 3. Well, a negative 4 divided by negative 3 turns into a positive 4 divided by 3. That's why I'm showing this here. But then I'd have to take the square root of 4/3 and then add 1 to that. Now, when we take the square root, since it wasn't written as part of the original problem, when we put that square root on paper, we've got to be prepared for both a positive and a negative result. And therefore, the x value would be equal to the square root of 4 over 3 plus 1, and negative square root of 4 over 3 plus 1. As a decimals, those are represented with these values here. We certainly could have used the quadratic formula with an a, b, and c value from the standard form, but this will work just as well. This obtains the exact same result. As far as the sketches go, I plotted my vertex at 1, 4. I knew that the graph would be opening downward and is 3 times as tall as normal, so normally we would step to the right 1 unit and then down 3 units, normally right 1 and down 3 to reconnect with the graph. We would step to the right 2 units and down 12 in this case, because what normally was 4 has to be 3 times as tall as that. So we have to drop down 12 units in order to reconnect with the graph, and so on. So that's the shape of the graph here, and you'll notice that the coordinate where the graph touches the x-axis isn't very nice. It was a nice coordinate here, 1 unit above, but it's not a very nice coordinate on the x-axis in and of itself. But that's okay, because the calculated results that we got for the intercepts seem to support our thought that it's just to the right of 2 and just to the left of 0 at 2.1547 and negative 0.1547. Now to finish out this video, I just thought I'd post one challenging problem and then one sort of vocabulary style question at the very end here. This is a bit of a challenge problem here. Determine the quadratic function whose vertex is at 1, -5, and whose y-intercept is at -3. We don't actually have the graph provided to us, so we're just going to have to trust our own work here. It's not provided on the next page. Well, let's think about what we've got. We know that the vertex is at 1 and -5, so in a sense I could create a function in vertex form. What I don't know is the a value out front. We don't know if this is a standard height parabola or what. But I do know that x minus 1 squared minus 5 would be the remaining components of the vertex form. With an h value of 1 and a k value of -5, we can write it this way. Now what we also know is the y-intercept occurs at -3. So the y-intercept is -3, and the y-intercept occurs when x is equal to 0. So if I replace x with 0 and f of x with -3, I now have an expression with all components shown in numerical value except for the letter a. And that's pretty easy to solve for. -1 squared is 1, so a times 1, which is just a, minus 5 is equal to -3. Therefore, a by itself is 2 after we add 5 to both sides of the equation. Well, now that we know that a is 2, and we already knew what h and k were, we can also say now that f of x in its original form must have been 2 times x minus 1 squared minus 5. And should we be asked to write this in standard form, we can do the same by expanding x minus 1 and writing it twice. Then we can FOIL and distribute, which would be 2 times x squared minus 2x plus 1 minus 5, 2x squared minus 4x plus 2 minus 5, and ultimately 2x squared minus 4x minus 3. And so here we have it, our equation in vertex form and the same equation in standard form, all of which was obtained by key components and not the equation at the beginning. And so the very final question for this video is to determine whether the quadratic function has a maximum point or a minimum point. So part of that question got cut off here. So whether this quadratic function has a maximum point or a minimum point. Recall that parabolas are the result of our quadratic functions, and they can either open up or down in this context. Of course, if we have a point that exists at the lowest portion of the U-shape, that's a minimum. If we have a point at the top, we would call that a maximum. So, does this particular function have a minimum point or a maximum point? Go ahead and make your best assumption, guess, or calculated result now. This graph has to have a minimum point. It has to have a low spot in it. And we know that because our a value is equal to 1. And when our a value is equal to 1, it's a positive value. It means that the graph opens up. And so when the graph opens up, there will be a low point or a minimum to that graph. So sometimes thinking about the behavior of a function without actually graphing it specifically helps us to answer some questions about the meaning of that equation. I know this video was quite lengthy, but the review of the quadratic behavior of quadratic functions is going to be an important one, and it'll be useful as the week plays out. So thank you very much for watching, and let me know if you have other questions.